morning, good afternoon, good evening, wherever you may be in this part of the world. And welcome to another session of my presentation. And this time, the topic is a very interesting topic. Yeah, this is a trend that you see on a daily basis. Okay, so the topic is how understanding how electric trains function. How does it work? My good name is John Kweku Amotu, and I've been an electrical engineer for the past 31 years, and I'm based in the United States of America. Now, the other thing that I would like to talk about is basically after watching this video, if you like the presentation, don't forget to select the like button in YouTube. And also, don't forget to share in YouTube. Also, don't forget to select the subscribe button. Below is my YouTube channel, and the name of the YouTube channel is Work and Happiness, Talking to the Engineer. Click here, there's a series of presentations out there that will help with your career and help young engineers out there be able to develop your career, because and also for your continuous learning at basically to develop the PDH hours for renewal of your PE license. If you already have the PE license, this can be a tutorial that you can also use it, to leverage your PDH hours that is required to renew your PE license. Now, let's talk about the different technologies of train that we have out there. The first one is the diesel locomotives, right? And before the diesel locomotives, we used to have the coal type, right? Okay, so before the diesel was the coal type, right? That utilize coal to basically the coal is burnt, and basically it creates steam, and it has a boiler, and basically the steam from the boiler is able to help propel the train. When we were born, I think that is one of the ones that I saw, in addition to the diesel locomotives. So at a point in time, both the coal-powered train and the diesel locomotives were basically running in parallel until at a point in time, basically the coal type was basically retired. And the coal type, as I don't know, many of you that were born in the 60s, those were the types that had basically mechanisms tied to the wheels that basically it moves, in zigzag, motion, and I think many of you that were born around that time, I think you basically figure out, what type of train that I'm talking about. Right? It's basically, the train has a fireman. They call it a fireman. Basically his job is basically, to shovel the coal and put it in the boiler, and the boiler has steam on the peripherals, and basically the boiler, the heat from the boiler from the coal basically hits the water and creates steam, and the steam is what propels the wheels, and the wheels has basically latches that basically helps it to move. Right. Okay. So next is the electric train. Right. Okay. So the electric train, we have different speeds. Okay. So I've seen the one that runs at 150 kilometers per hour, right? So that can be used to basically travel from city to city, and it can also even within the city, let's say depending on the stretch of the city, if the city is so wide that basically stretches from one end to the other end, then up to 150 kilometers hour electric train can be used, and that is what you see in most of these cities. If you happen to be living there, or you take a vacation into cities that have a lot of this electric train. Next is the fast super electric trains, and basically they have a speeds of about 250 kilometers per hour and about 365 kilometers per hour, right? Okay, so these electric trains are super fast, and basically they utilize them from city to city. If you go to Europe, especially Germany, you'll see a lot of these trains, and basically traveling from city to city, traveling from country to country. Matter of fact, um, I've ridden in one before, and basically it can move, sometimes about 250 kilometers per hour, 280 kilometers per hour, and I've seen ones that basically run about 365 kilometers per hour. These trains are super fast, and matter of fact, they've been built in an aerodynamic way. So if you see the frontal part of the train, it looks like an aircraft, in front of the aircraft, right? So that's how it's been built, so that it basically facilitates and enables the dynamic, basically the dynamic part for it to be able to float and basically move very fast. Next, magnetic levitation trains, and this is the latest technology, and that is the super fast train that travels faster than an aircraft, right? Okay, so these are the countries that have basically wanted to put it into commercial, some of them have put it into commercial operations, and in a process of basically going above and beyond to expand it, let me put it that way. So US, Japan, China, and Russia have all come up with magnetic levitation trains. And Japan, for instance, is expanding the train stations for these trains, fast trains. Think about a train that moves as fast as 605 to 620 kilometers per hour. That is even faster than a commercial aircraft that travels from country to country. The Boeings that you see, right? The Airbus that you see, right? Sometimes you'll be sitting in an Airbus or Boeing, then maybe at an elevation of altitude of about 30,000 meters or feet, then you see it's basically its speed about quite close to about 586. That's what I've seen, right? Kilometers per hour. Comparably, look at this magnetic levitation train that basically travels at 605 kilometers per hour to 620 kilometers per hour. That means that this train basically travels faster than a commercial aircraft. Okay, so that is a disruptor, a breakthrough in technology for these trains to basically be utilized traveling from country to country. Yeah. The next thing that they have to basically put in place is for it to be able to be achieved, traveling over the ocean or under the ocean, which will facilitate traveling from continent to continent. Yeah. But now it travels within the jurisdiction of each country that has put it in commercial operation. That is United States, Japan, China, and Russia. So, what is the technology, right? Basically, it utilizes super magnetic conductors, right? Conductors that are highly charged. The magnetic field is so strong that basically when it starts moving, right, you have basically cryogenic technology on board that is able to cool the magnet that is the superconducting magnet to about negative 150 degrees Celsius, right? So the train basically has rails, then it starts moving on wheels. Remember, before it reaches a certain speed, right? 150 kilometers per hour. That is the baseline speed, right? That it travels just like an aircraft, about to take off, right? Same technology. Remember, an aircraft, when it is about to take off, right, it taxis along the runway, right, until it starts increasing the throttle, yeah, gears, where basically they call it throttle valve, where basically the speed increases. So usually when you're about to take off, you see that the captain basically increasing the throttle to increase the amount of fuel that goes to the turbines, right, to be able to put enough thrust, right? So that is when the speed increases until it reaches a threshold speed. Then the pilot basically lifts the yoke, right? That's a little yoke, that U-shaped thing in the captain's cockpit, right? So all that the pilot does is after the plane has picked up that speed up to that threshold, then that low lift of the yoke is the one that basically allows the plane to creates that lift for the plane to be able to lift and start climbing. Right? So the same technology is with this magnetic levitation trains, right? So as the train, you have the tracks, right? And you have the train, which has wheels on it. So it moves on the wheels up to about 150 kilometers. Then after 150 kilometers, basically the wheels or the tires start retracting, just like an aircraft. As an aircraft about to take off, right? It lifts, it creates the lift, and the airflow on the wings is what basically facilitates, enhances the lift, right? Then the tires starts retracting, right, to reduce the drag and be able to create more lift. So same philosophy, right? So the tires will start retracting and go into a carriage inside the train after speeds of 150 kilometers per hour has been exceeded. So at that point, that is when the superconductors technology on board the train is supercharged. Then the train starts levitating. Levitating means that it is basically floating about 1.3 inches to 3 inches above the tracks. So what do you see, right? It means that there's no friction compared to the traditional electric trains, the diesel locomotives that you see, right? The traditional diesel locomotives, right? The wheels basically are running on the tracks, right? So that itself, it's a deterrent. That is what the friction is, what reduces the speed. So that is why that technology, the maximum speed they've been able to achieve is about 360 kilometers per hour, right? So if you are able to remove that friction, cause of friction, right, from this, then that is how magnetic levitation trains, also known as maglev trains, are able to achieve the fast movement up to 620 kilometers per hour. People, that is faster than an aircraft. That is faster than an A320, Airbus A320. That is faster than Airbus A380, right? So think about it. Right? So because there's no friction and it's just floating, it's just floating on the tracks, foam or whatever, moving from within the city to city, right? And the goal is for this technology to be implemented so that it can be able to travel from country to country, right? By building tunnels under the ocean, right? And implement their magnetic levitation train technology. Okay, so that is a brief description of their technology, how the concept of that technology, right? Yeah. So it utilizes superconducting magnets, and basically that's how it's able to. So it propels, moves forward, right, based on magnets. North south pole, north south attracts, north repels, south repels. So that's how the movement, propulsion, that's how it propels forward, right? Based on that, right? Then it also has side magnets, right? Okay, so you have superconductors on the carriage, right? Then on the side of the track are also magnets. North south. So that is the one that helps the train to keep the train in a straight line. Let's say if it is moving, just like an aircraft, right? Just like an aircraft, right? The goal, what the pilot does, is to keep the nose of the aircraft in line with the GPS line that the pilot sees in the cockpit. Same thing. So the goal of those magnets on the side of the track and the superconductors on board the train, basically, they attract, repel, and try to guide the train to move in a straight line. So that is what the magnetic levitation train does. Okay, propel, lift, and lifting. I think I explained to you, how the lifting is done. Matter of fact, I'll create a different presentation on magnetic levitation train. So maybe that will help you to understand more how these maglev trains and the technology behind it. So next is the types of electric trains, right? Okay, so electric train, we have two technologies: the DC traction motors, right? Then AC traction motors, right? Okay, so the DC traction motors are mostly utilized in smaller cities, where and most of the third world countries, utilize these DC traction motor, right? And it's based on, I'll say, location and cost and how easy, familiar, they are with that technology. Next is AC traction motor, and that is what you guys have seen a lot in most of the cities in advanced countries, right? Okay, so the reason being that DC traction technology was the one that started earlier, right? And that technology was there before AC traction motor came, and basically, so depending on the country, if the country is so familiar and still wants to continue utilizing DC traction motors, then they allow that technology to stay, right? And next thing if they want to move away from those DC traction motors based on certain attributes, which I'll explain in the next slide, then they can decide to change out those DC traction motor technology to an AC traction motor technology. Okay, so now Let's talk about the types of train technologies that we have. We have the DC traction power electric train and the AC traction power electric train, right? And like I indicated, some of the developing countries still utilize the DC traction power electric train, and it's all based on also the distance that if it travels within shorter distances, some of even developed countries still utilize DC traction power electric train. But most often than not, developed countries utilize the AC traction power electric train based on the significant attributes of the AC traction power electric train compared to the DC traction power electric train. Okay, so now let's take a deep dive into the attributes. Okay, so the first one is basically for voltages of 300 volts to 3000 volts DC, right? You can utilize a DC traction power electric train. And sometimes for voltages up to about 900 volts DC, some of the countries utilize a third and a fourth rail, right? A third and a fourth rail, right? So basically you have a first and second rail where basically the train rides on, right? And on each side, right, you have the third and the fourth, right? So the third and the fourth will be the power supply conductors, right? The positive and your negative, right? That provides power to the train. But for voltages above 900 volts, right, DC, then the best technology to utilize based on cost effective and optimization is overhead catenary system, right? Okay, so the other one is a high starting torque, right? Based on the DC series motor technology, right? Next is it allows a rapid acceleration, right? And that is great for the DC power electric train to pick up speed. Then it also allows rapid braking. If you want to basically, break the speed of the train, then you can utilize the DC train. So that itself tells you, why it is utilized within the city limits, right? Shorter distances, right? Because of the need to be able to break all of a sudden. Next is it costs less, right? Then less energy consumption, then less space or footprint, right? Based on the DC technology, right? Next is less electric interference, right? Because of it has a less magnetic field that will not interfere with communication circuits and other electric circuits, right? So that is one of the greatest attributes of the DC traction power electric train. Next is because it requires substations every 2 to 3 kilometers, and it's just based on that technology. Sometimes, it becomes very challenging to achieve that within a city that has a high density of population, and sometimes you have to utilize underground substations. Next is the AC traction power train, right? Okay, so this technology is based on the fact that 50 kV voltage can be achieved based on a frequency of 16.7, right? Okay, so this utilizes a frequency converter, right? That converts the nominal frequency either from 50 hertz or 60 hertz to 16.7 hertz to be able to cut down the cost of material, right? Conductors, equipment, size. That is why the frequency is reduced. Then for voltages of 25 kV, the nominal frequency is utilized, either 50 hertz or 60 hertz, right? And one of the greatest attributes, or I would say an attribute that has propelled it, and has been a disruptor and a breakthrough for this technology, is the easy ability to be able to step up and step down the voltage by utilizing a step-up transformer or a step-down transformer. And the easy control of AC voltage, right, based on the variable speed technology for AC induction motors, right? So that is how most of these AC variable speed drives basically, came into. Then the other breakthrough attribute is it allows substations to be built at 20 to 30 kilometers. So basically, what does this do? It helps you to utilize this technology to achieve city to city travel, train travel, country to country train travel, right? Because it stretches the need to be able to build substations, right? Okay, for AC traction power, you can build substations up to about 30 kilometers, right? Whilst for DC, you have to build it within 2 to 3 kilometers, and so that is why the DC traction power technology is utilized within the city limits, within very short distances, and most of the substations are located underground. Next is a reduced capital cost. Okay, so next is a beautiful picture of an electric train. So this is what you see out there. If you're living in a city that has a lot of these electric trains that move on every minute, 2 minutes, 3 minutes, right? Okay, so you can see it over here. This is what they call the catenary, right? Catenary, right? Okay, so basically this one is a non-conductor, basically that stretches the entire length of the travel of the train, right? And it has weights that are basically at various vantage points. Let's say every stretch of every 2 to 3 kilometers, it has weights, right? That hang, right? That helps to basically prevent these catenaries from sagging, right? Okay, so this one also it's the support structure for these catenaries, and below the catenary is the actual live conductor, right? A single phase, right? And this is the conductor coming from the train. So this is the simplest design for you to understand how these work, right? But in reality, they utilize a pantograph, something they call like a pantograph. I'll show you how the pantograph utilized. So this one is just for you to understand how this works. So this is the conductor from the train, right? That's a copper material, right? And this one is the conductor, the live conductor, right? That has whatever voltage, let's say 25 kV, right, on it. And this one is just a non-conducting support conductor that has weights. This conductor also has weights, right? Basically, its goal is to prevent the live conductor from sagging. As you know that copper, when it gets heated up, especially if you have an extension of temperature limits. Let's say during summertime, you have temperatures are basically escalating, right? And basically increasing. Then this copper material tends to heat up and sag, right? So the goal of these weights that has been installed at various vantage points along the entire length of the track, let's say every 2 kilometers, is to keep the conductor from sagging, right? But it cannot completely eliminate this sagging, right? There's going to be some sagging, right? So what this catenary conductor does is it helps. It has basically some conductors that are, basically they are non-conductors, right? And basically fixed like this that helps to keep these live conductors in place, right? To basically prevent, let's say, if it is allowed to, let's say, 3% sagging and keep it straight, right? Okay, so it has insulators right here, right? And this is a non-conducting part over here. Okay, so next is basically, how this technology works. Okay, so the goal is this is a live conductor, like I explained in the previous slide, right? At 25 kV AC voltage, right? And this is your copper conductor that is connected to this live conductor. So this live conductor runs the entire length of the track, right? And this is an induction motor, right? Okay, so the required voltage for the induction motor is 1000 volts to 3000 volts, right? Okay, so what does that mean? It means that I should have a transformer that will step the voltage down from 25 kV to 1 kV to 3 kV, right? To be able to provide the required voltage to this induction motor that is installed on the wheels of the electric train. Okay, so this is the configuration of the wheel of the electric train, right? So the motor is what you see over here, right? This is the induction motor, right? And this is the wheel of the electric train, right? Okay, so you have 25 kV from the live line that goes through a transformer that steps it down to, let's say, 3 kV or 1 kV and provides that voltage to this induction motor, right? So as the voltage is applied to the induction motor, right, and basically it helps the wheel to turn, right? So these are the copper bars. As you know, the induction motor has a stator, right, winding, and it has a rotor that basically consists of bars that are basically skewed, you know, in an angle, right? And the goal of the skewness is basically for harmonic cancellation. That is one of the, as you can see, it goes at an angle. They call it skewness, right? Is to mitigate those harmonics by providing harmonic cancellation, right? Okay, so this is the wheel, right? Okay, so the wheel basically goes right on top of the track, right? The track itself is basically, you know, a material, non-conducting material, right? Okay, so that is the ground plane, right? I take it back. It's a conductive material. It's a ground plane, right? Okay, so the goal is basically you provide voltage, and you should be able to provide a return for the voltage, and that goes to the ground, right? Okay, so at various sections of the entire length of the railway line, there is a grounding section, right? That allows and these grounding sections are in short distance, right? That helps basically the voltage to flow in and return, flow in and return. Okay, so this one is a much closer look, you know, of the induction motor, right? So this is the induction motor as it rides on the wheel, right? And this is the terminal that basically the voltage comes from, right? Okay, so 25 kV is stepped down to about 1 kV or 3 kV. And it comes here, then it provides the voltage to the induction motor, then it rotates, then basically it should have some brushes here that helps basically to provide the return to the track, right? And that is grounded at various points along the entire length. Okay, so this is a much deeper picture that shows your overhead line, right, at a voltage of 25 kV AC, right? And you have your conductor, right? Okay, so then you have your transformer that steps the voltage from 25 kV to 1 kV and has a terminal there that provides that voltage to the induction motor. The induction motor rotates, then the voltage comes back and goes to the ground. That's the ground return. And like I indicated, the ground return is at various vantage point that has been probably not more than one every 1.5 to 1 kilometers along the entire length of the train tracks. Okay, so remember I made mention that okay, so this is your 25 kV line. This is your conductor from the top of the train, right? Okay, so actually this one is the simplest one, but in reality it's in the form of a pantograph, right? Okay, so inside then it goes to a step down transformer, right? So then from there you have 1 kV or 3 kV. Then on this side is the brushes right there that I indicated. That helps basically the connection from the voltage that comes in to the wheel, right? Before it goes to the ground plane, right? This is how it looks like. Okay, so remember I made mention that you have a voltage of 25 kV, right? That is too high for you to apply that amount of high voltage to an induction motor, right? An induction motor requires a voltage of about, let's say, up to 3 kV, right? Okay, so what do you have to do is to step the voltage down, and this is done through this equipment here. This is a step down transformer, right? So you have the primary side and you have the secondary side, right? Inductively, they are coupled together. So you apply the voltage here, 3 kV or 1 kV, and basically it creates a current through the winding, and once the current is developed, it creates a magnetic field. That magnetic field is what links this secondary coil to create an induced voltage. So this induced voltage is what is fed into the induction motor to propel it forward. Okay, so next is another visual picture that basically helps you to see the whole part. Okay, so you can see over here, this is your transformer, right? I come in with 25 kV, right? Then I'm able to achieve a 3 kV or 1 kV. Then I feed that into this motor, right? Motor turns. Then after that, provides that return path to ground. Okay, so now, okay, so you can also have a three-phase arrangement, right? Okay, so what I showed you is the single-phase arrangement, and is the most ideal picture. You can also have a three-phase, but if a three-phase configuration will cost, right, and also its efficiency compared to the single-phase, it's not much to be desired, right? Okay, so this is where the wheels, right? You can see on the train, right? You have different sets of wheels, and this is where the transformer is located, right? So you have a 25 kV that comes in phase A, phase B, phase C, right? That comes in, it goes through the transformer, it goes to the primary side, then from the secondary side, it comes to the motor, then from there, the return goes to ground, right? So if the three-phase configuration is not much to be desired, and the single phase is something that rather is much to be desired, then there has to be a technology that can convert from single phase to a three-phase configuration, and that one is done through converters. Okay, so remember I indicated that sometimes you have a three-phase and a single-phase arrangement, right? You have a single-phase and a three-phase arrangement, right? Okay, so it is much efficient, much reliable to utilize, and also cost, to utilize the single-phase arrangement compared to a three-phase arrangement. And I showed you how the three-phase arrangement looks like, right? Okay, so that means that if you choose to utilize the single-phase arrangement, it means that you have to convert it to a three-phase arrangement for you to be able to provide a three-phase voltage to the motor, right? The motor requires a three-phase voltage, right? Okay, so I come in here with a single phase, right? Then I feed it to my primary side of my transformer, right? Then I step it down to 3 kV over here. Then from there, I feed my rectifier from here. The rectifier basically has diodes that basically rectifies the AC sinusoidal voltage to a DC voltage equivalent, right? So this should be a DC bus that has a capacitor that helps to keep the DC voltage before it comes to an inverter, right? That inverts the voltage to the AC equivalent before it provides that voltage to the three-phase voltage to the induction motor. Okay, so next is basically the whole part. This is how it looks like. Okay, so I come in with my 25 kV, right? Okay, then I go back to the ground, right? And I indicated that, the ground is basically strategically located at various sections, let's say between 0.5 kilometers to every kilometers, and along the entire length of the track, right? So once I impress this amount of voltage on the primary side, this is the primary coil of the transformer, right? And this is the secondary coil. I create a current, right? This current creates a magnetic flux that flows and links get coupled to the secondary side to create an induced voltage, right? So that induced voltage is what is fed to the rectifier. And what does the rectifier do? It rectifies the AC sinusoidal voltage to a DC equivalent that is kept stiff with a capacitor. Then you have an inverter that inverts the DC voltage to an AC voltage equivalent. Then the AC voltage, three-phase AC voltage, is fed to the induction motor. Right? So this is the whole scheme of how electric trains work. So beautiful. Okay, so after applying voltage to the induction motor, right? The induction motor has a speed, right? Okay, so let's say the induction motor has running at a speed of 1600 RPM, or let's say 800 RPM, right? How can I amplify this speed to make it run faster, right? So I can have a gear system, right? That will multiply. As you can see, this is a smaller gear that is coupled to a bigger gear that will basically amplify the speed, let's say 10 times, right? To achieve a faster speed, let's say 8,000 RPM, right? So to make the train run faster, that's how the speed multiplier is done in the wheel, right? So this gear is inside the hub of the wheel. Okay, so remember I made mention, what I've shown to you is the most simplest ideal connection to the overhead conductor, right? Overhead line or conductor, right? 25 kV, right? And the picture that I showed you with a single conductor hanging off the roof of the train, right, is the most simplest and ideal situation, right? But in reality, this is the actual picture that you see on top of the train. They call it a pantograph, right? It goes up and down, right? So they call it a pantograph, right? Okay, so, and it's operated by a pneumatic system, right? The pneumatic system is what helps it to move up and down depending on the level of this overhead line. Remember, you are traversing this entire length of this overhead line catenary system, for several kilometers, thousands of kilometers, right? Okay, so the length and the height of these overhead lines, sometimes might change, right? Depending on the route, right? So sometimes the pantograph has to come down, right? Be able to make contact with the conductor in that area. So that is what this pneumatic system helps it to regulate its height by moving up and down. And also it has this shape to help it basically move a little bit on a radial level, right? It moves like this. It moves like this. The goal is to prevent a wear on this surface and also a wear on this conductor surface. So that is why they don't allow it to ride at one particular place, but for the riding to vary, along the few length, from here to here, it varies, so that basically it evens out the erosion on the conductor surface. Okay, so now let's talk about providing an auxiliary power to the train, right? How do we provide an auxiliary power to the train. Okay, so inside the train, right, definitely you should have a battery system, right? You should have a battery system, right? That should provide an emergency power, right? Okay, you should also have a generator, an auxiliary generator that should be able to provide auxiliary power to the train, lighting, etc., fans, etc., and basically, for other power sources for even, cooking inside the train, all the services that is run in the train. That is where the auxiliary power source come from. So you have a gear system that is connected to the one of the wheels, right? This one is a different wheel from the one that has the induction motor, right? That helps it to propel forward, right? But this one actually has a gear system that is connected to a generator. So as the train is moving, it is also generating electric power, right? So that electric power is the one that provides power to the train. So it's called a self-generated power. Okay, so now let's talk about something beautiful, right? You ask yourself, how does a train brake? How does that technology work, right? It's called regenerating braking. Regenerating braking, right? So regenerating braking, what are you doing, right? So what the conductor, right, or the person driving the train, right, basically, pushing, the train forward, what it does is the supply voltage, right? If it is 3,000 volts, right, what it does is he reduces the supply voltage to about 2,000 volts, right? So when he does that, right? Okay, let's see this way. You have 2,000 volts being fed, right? And you have a magnetic field that has already been generated, right? Based on 3,000 volts. So basically, that magnetic field ends up canceling that already generated magnetic field and basically generates a current that flows to basically provide a braking mechanism to slow down the train, right? And after that, the manual braking can be applied, right? So as you can see over here, the magnetic field is changed when the supply voltage EMF is changed, which basically reverses it, and it ends up canceling the existing magnetic field and provides an induced current that will flow in a different direction to offer a braking scheme to it. So in reality, this is how it works, right? This is the pantograph, right? Okay. So the pantograph has support insulators. So this is what you see on top of the train. The train, you see it right here on top of the train, right? So it has insulators, right? That supports this live mechanism, right? This is the live 25 kV line, right? So that comes in here, and believe me, this is more of a miniature substation, right, on top of the train, right? So it has circuit breakers, right? So imagine a circuit breaker that is handling 25 kV and 3 kV, right? Then it has surge arresters, right? All over here. Then from here comes in your 25 kV, comes into your transformer, right? And which is basically fed to your converters, right? Okay. Next is basically how this entire length of this catenary system looks like. Okay, so as you can see over here, this conductor, live conductor 25 kV line is not straight, right? It's zigzag, right? And there's a reason for that, right? It helps basically, like I indicated, this surface and this surface to basically revolve around different surfaces to prevent basically friction, corrosion, and basically eating the surface of this conductor and the surface of this conductor, right? So that is why it has that shape, that zigzag shape at different points to help facilitate that. Okay, so this is another picture of the induction motor. As you can see over here, it has the stator, it has the rotor, right? And basically, on a small scale, this is how it looks like. Then this is the part of electric voltage, the current flow, right? It comes in and goes through your rectification, and it comes out and it flows back to the ground, right? Okay, and the ground is at various voltage. Lastly, it's regenerative braking, and I think I explained what regenerative braking is. Basically that is what the operators of the train basically apply by reducing the applied voltage to the motor, induction motor, right? Okay, so let's say if it is a 3 kV, the operator of the train will reduce it to, let's say, 2000 volts, gradually reduce it for 2500 volts. Then basically what it does is basically you have a counter, EMF built, and basically they cancel each other and create an induced and basically regenerating brake power and torque that basically helps to slow down the train. And later on, the operator can basically apply the manual brakes to bring the train to a stop. Okay, so with that comes to the end of my presentation, and hopefully you can check out my YouTube channel. And if you like this presentation, don't forget to select the like button in YouTube. Don't forget, and subscribe to my channel in YouTube, right? Work and Happiness, Talking to the Engineer. That's the name of my YouTube, and it has many tons of presentations out there that will help you develop yourself, help you if you are preparing for interviews. I have a list of typical questions that will help you prepare for your interview to boost your confidence. And for you young engineers out there, basically has a lot of presentations that basically helps you to keep your learning and continuing education basically very active. Yeah. With that comes to the end of my presentation, and thank you so much, and look for another interesting presentation on another high-speed train, magnetic levitation trains. This is the train that travels even faster than an aircraft. A commercial aircraft are flying from country to country, right? This train travels faster than that, 603 kilometers per hour.